So, we're now going to move on to do the problem of characteristics. So for the second order equation, for the wave equation, you've only done characteristics for first order. You might have done them for second order, but I don't think you have. So it's going to be tricky because we're going to do characteristics for second order and we're going to do them non-linear. So you haven't done the characteristics for just the normal wave equation. So let's just have a look at this here. So maybe, this isn't in the notes, but it might be kind of useful just for 2 seconds. But we don't really have time to, unfortunately, talk in great detail about characteristics for that. But the characteristics here are x equals plus or minus t. Okay, if we had a c here, then it will be x equals plus or minus ct. So there's 2 sets of characteristics, second order, or it's a system of 2 coupled. Remember we had the 2 variables which we're going to have here, or 2 variables, gives rise to 2 characteristics. And you need to have the solutions carried on both. You can't solve unless you carry it on both the characteristic lines. You can't work out the solution. Okay, let's leave that. Let's get rid of that. Okay. All right. So let's do the characteristics for our problem and try and understand this. So this is not too scary. So the system of equations we wrote down was this. It was 2 dtc plus 2u dxc plus c dxu equals 0. And it was dtu plus u dxu plus 2c dxc equals 0. So if we add these 2 together, what we're going to end up with is we're going to end up with d by dt of u plus 2c plus, we're going to get this thing here, we're going to get u plus c times d by dx of u plus 2c. It's not obvious that you'd write it like that, but you can sort of see all the terms here. The time derivative of u, that's there. Time derivative of 2c, there's that. You've got u times dxu, that's here. You've got u times dx of 2c, that's here. And you've got c times dx of u, and you've got... Alright, and if you subtract, you get the opposite. If you subtract, all you get here is a minus appearing here, a minus and a minus. So what this tells us is that on the characteristics given by dx plus dt equals u plus c, the quantity u plus 2c is a constant. It's quite a powerful statement. And then on the characteristics, dx minus dt is equal to, where u is equal to u minus 2c, u minus 2c is a constant. So we're far from able to solve the system of equations. But we are going to get somewhere here. We've got to do a few more simplifications, and we're certainly not going to get a formula for the general solution from this. And if you can just solve this problem by time marching along these characteristics, then you've got to be super careful about it. So we introduce some notation here just to help us out. So we call this curve, the curve that solves that equation we call C+, that's the curve. And we call this curve here C-. So that's the curve. And we call this invariant, this constant, we're going to call R+, and this constant we're going to call R-. I'm not sure how much we're going to use that notation. Okay, they're called the Riemann R+ and minus, which is U plus or minus 2C are the Riemann invariants, the Riemannian invariants. Alright, so how the heck can we solve this equation? Now this is where it's going to get a little bit tricky, and I'm going to illustrate it through some examples and some pictures, because we're still far from able to solve these equations, because it's not a formula that depends only on x and t like we had in the case of a simple wave equation. These are going to get bent and twisted around because this quantity here is different from here. So the curves don't have to be, they're going to change dynamically in time, and of course they're going to cross and meet and form shock waves. Just one thing here is that, okay, you can sort of see here that for a solution we need one of each characteristic. Okay, we don't want two characteristics, we don't want two x pluses, we want an x plus and an x minus at each point. Okay, we want an x plus times 1, only one of them, and an x minus times 1. We don't want two x pluses coming together, that's going to be a shock. And likewise, we don't just want only x pluses. We need the x plus and the x minus, because then we can go, we know what the value of this number is, and we know what the value of this is, and we can solve that system of equations. So maybe that's so we're going to get u plus 2c is equal to 8, say, and u minus 2c is equal to 9. And we can solve that system of equations and we'll find u and c. And that's really a helpful way to think about how the system of equations is going to work. So we know these are a constant, we're going to trace them back and find their value. They started out with a value of 8, so it must be true they're always equal to 8. We trace these back, they had a value of 9, and then we can solve the system of equations when you get u is equal to what? Right? If I add them together, I get 2u, so u is 8.5, right? And c must be equal to minus a quarter or something like that. Right? So you've got, maybe not a great example because c can't be negative, but so something's gone terribly wrong here if that was the case. So let's make that equal to 7. Okay, then we get a nice answer here. Okay, or equal to 6. But you can see how we're going to be able to solve this system of equations as long as we can do that. So what we're going to do here, I've gone through all this derivation. We've got a long way into it, but we've got to find the equation for these curves, and then we've got to trace back on those curves. We know this is a constant. We trace it back to the start, and then we compute, and then we calculate the answer.